This set, natural number, we call it countable infinite. And then all the real number between 0 and 1 is called uncountable infinite. Then the natural question, which set is bigger? By Cantor, basically it says that the number of things in 0 to 1, that means include 0, 1, 0.01, 0.001, 0.0001, 0.0001. I can talk for a whole day, non-stop forever until the universe explodes. Still, I cannot finish. This set have more stuff than 1, 2, 3, 4, 5. How do you prove it? Basically, this picture is a proof, but let me explain. You have a number A, you can always write down as a bunch of stuff add together. So for example, I have 10.7. Okay, this is same as this -1 times 7. So this means what? This means decimal place 7 plus what? 10 to the power 0. That means 1, 2, 3, 4, 5. Okay, 0 plus 10 to the power 1 times 1 plus, this is the 10, right? The 10 plus power 2 times 0 plus and so on. What does it mean? It means this number, I can write it in something called vector form. So it's a 7, 0, 1, 0, 0, 0, 0, 0, 0. So what does it mean? You think of a three-dimensional coordinate space. This coordinate is all the 10 to the power -1. That means all the decimal point, and you have a bunch of coordinate here. This coordinate is all the coordinate of 10 to the power 0. That means 1, 2, 3, 4, 5, 6, up to 9. This coordinate is all the power 1. So what is 10.7 here? It will be x coordinate go to 7, y coordinate is 0, z coordinate is 1. So it will be this point. So it means I have a 3D thing, I have an object here. So that means 10.7 in a three-dimensional coordinate system is a point located here. Well, all number can be written like this, right? Suppose you have pi 3.141 whatever thing, right? Then if I want to do this, the decimal place, let's say I just consider up to 1 decimal place, it will be 1, the second is 3, and then there's nothing here, right? Then 0. So pi in this coordinate system is 130. 1, and then y is 3, 1, 2, 3, z is 0. So pi will be here. And since these 2 points are in different locations, they are not the same point, so these 2 numbers are not the same number, right? Or in other words, if I write a number, let's say 1.2, 3, 4, 5, 6, 7, 8, 9, 10. This is the same as I have 11 number. So I have an 11-dimensional vector space. And each of these number is a coordinate in this particular space. And it represents a dot in that space. And if I suddenly change one particular coordinate, it represents I have a dot shift in one particular position, right? And if I shift one particular position, let's say I change this to 5. Everything is the same. Then now I call this A, I call this B. Of course, if I shift a little bit, these 2 numbers are not the same, right? This is the main ingredient in the Cantor's diagonal proof. So once you got this, here's the whole story. He said that this set, number element, is this Jewish letter, is larger than all the possible natural number. So how do you do that? So all the number between 0 and 1, you can always write it as, because 0 and 1, right? So we start with 0, in the end it's 1, but anyway. So it will be 0. First digit, second digit, third digit, fourth digit, sixth digit, and forever, right? And then you just write down a list like this. All the number I can write in this form, right? So for example, I want to write 0.5. Then it will be what? 0.500000000, right? So in this case, this is 0, this is 0, my A11 is 5, my A12 is 0, and then my next number is 0. So this is just a particular number in this list. What about 0.7? Same, right? What about square root half? That means 1/4. That means 0.25. Same, right? It will be somewhere here. And these are all possible real numbers. Okay, let's say this is true. Then the idea is very simple. Let me recap. How do you show 2 sets are the same? You show 2 sets are the same if you have the red figure. This Cantor basically want to say that I have a 1, 2, 3, 4, and if this whole picture is complete or true, then this is N, this is R, then I have this, then bijective, same size. Basically, Cantor says, no, something here cannot be represented here. That's the idea. He basically do the following. This one is very important. As I told you, if you shift one particular box, these 2 numbers are different. So that means I just need to make a new number. Let me call it new. And then what? First is 0 because I have to make everything in 0 and 1. So what I'm going to do, for the first digit, I just have this digit plus 1 here. Then, because this digit have shift, this new number, I don't need to look at everything else. This box is already different from the first digit in x1. So new and x1 cannot be the same, right? Then I want to make this new number different from all possible number here. So for the second box, I will going to take this number plus 1. Because these two boxes are different. So this new is different from x2. If you don't remember this, if I have one box is different, immediately I don't need to check the other box. They are different. Then what is the whole idea? I just keep looking at the diagonal and I plus 1 or minus 1. And then I put this into here. Okay? And this list is infinite. Doesn't matter. I can always do this. Then I have created a new number that does not belong to this list. So in other words, I have an n here, which is 1, 2, 3, 4, 5, and then I call it x1, x2, x3, x4, x5. I want to construct this, but now I'm showing that, okay, there's a guy called new here, is not here. That means this set is bigger than this set. I mean cardinality. That's the proof. So basically the idea is you create a new number by looking at the diagonal of this table, and you just take each of the box here to make your new number. In the process, you plus 1 in all the box. The plus 1 means that you want to make it different from each of the row. And then in the end, this number will be different from all the number here. So this number do not exist in this table. So that means something in R cannot be mapped up by n. So this, okay? So therefore, this infinity is bigger than this infinity. And this infinity we give a name, okay? And this infinity we give a name, okay? And this infinity is bigger than this infinity. And then now let me tell you what's the hardest problem in the mathematics. Is 2 to the power n0 equal to n1? The answer is you cannot tell. There are people prove that you cannot know this. That means what? This problem cannot be solved. And then what about I have a number that like this 2 to the power this set, Cartesian product this set, and then I take the cardinality. Infinity, in principle, you cannot do computation, but now you can. So this set is infinite cross infinite. Is what? It's exactly the snake picture. As I told you, this guy and this guy have the same cardinality. So this is how you get this equal sign. And this n is by definition this symbol. So that means what? This is the answer of you have a infinite dimensional cube, and the cube is infinite dimensionally big. And then how many points here compared to 0 and 1? It turns out this is more. Yeah. This is also insane. Suppose you have a set, the stuff inside is different infinity. Here's a funny thing. This is not even a set. Can you talk about the size of this? No. This is something that we cannot talk about in set theory. This do not fulfill definition of a set. What's the definition of set? The ZFC? No, you are saying the set have cardinality countable infinity or uncountable infinity. The cardinality of this is neither countable infinity and neither uncountable infinity. The cardinality of this is undefined. And now crazy thing, two mad people have this will prevent all this madness I just said. That means under this situation, if all your sets fulfill all the things like this, everything is safe. If these are all true for a set, that is a legal set. You won't have Russell paradox. Actually, this is the one that kills Russell paradox. This is the thing I'm not going to test in exam. This is insane. Let me tell you a funny thing. Who will study this? People in philosophy department.